In this video, we're going to talk about Avogadros Law. Avogadros Law is actually what led us to the development of the mole. So this is going to be a mole to volume relationship. It states that when the pressure and temperature are held constant, the volume of a gas is proportional to the number of moles present. In other words, the more stuff you have, the more room you have to have in order to store it. This is a direct proportionality. If one quantity increases, the other must increase as well. Another way to say that is if I take volume, divide by the number of moles, that's going to equal a constant. And N is what we use for our number of moles. So volume over N is equal to a constant. Now, if the moles of a gas in a cylinder increase, the volume needs to increase. So in this container, we have a 1 liter cylinder with 1 mole. If I add 1 more mole of gas, my volume must double. And we can set up another equation just like Charles's law and Gay-Lussac's law and Boyle's law, where we have V1 over N1 is equal to V2 over N2, initial and final conditions. Now, a lot of times we want to make sure that our gases are being compared, and in all honesty, the V1 over N1 is equal to V2 over N2, not a very common use of Avogadros law. But that being said, we have something that's going to be really super useful, and that is the concept of the STP, standard temperature and pressure. Standard temperature and pressure is 1 atmosphere, or 760 millimeters of mercury, and 0 degrees C, or 273 Kelvin for temperature. Now, what's really important is what happens at STP. 1 mole of any gas at STP is going to occupy a volume of 22.4 liters. This is what we call the standard molar volume. What this means is if I am at STP, I can use this molar volume to determine the number of moles of gas present. That is hugely important. So as I said, Avogadros law is actually where we get the concept of the mole. If I have two balloons at the same temperature and pressure, and they have the same volume, if those two balloons are exactly the same volume at the same temperature and pressure, that means they contain an equal number of particles. So if this is nitrogen and this is helium, this contains 1 mole of nitrogen, which is 28 grams of nitrogen. It's 22.4 liters at STP. We have to make sure that that is at STP. That is 1 mole, 6.02 times 10 to the 23rd, Avogadro's number of particles. And it's the same thing for helium. 22.4 liters, that's 1 mole of helium. That is 4 grams of helium, not hydrogen, that would be bad. Helium. And then 6.02 times 10 to the 23rd particles. So we can always use our molar volume as long as we are at STP to find the number of moles of a gas. So let's do a problem like that. How many moles are contained in 2 liters of N2 at standard temperature and pressure? So I get a volume is equal to 2.0 liters. I know I'm at STP. So at STP, what do I know about volume at STP? 1 mole of any gas at STP is equal to 22.4 liters. So in other words, I can actually turn this into a conversion factor. 1 mole over 22.4 liters times our initial 2.0 liters. Liters canceled. That tells me I've got a number of moles, which is equal to 0.0892 moles of nitrogen. All right. So from here, you should move on to the next gas law, and that is the ideal gas law. The ideal gas law is going to allow us to do more stoichiometry, dealing with moles, kind of like Avogadro's, but in a much more controlled fashion. The ideal gas law is actually, you can use the ideal gas law to derive every single other gas law. So let's see the utility in the ideal gas law in our next video.